Hello, everyone. In this work, I'll talk about adversarial load of large numbers. This is a joint work with Noga Alon, Omri Ben-Eliezer, Shai Moran, Moni Naor, and Eilon Yogev. So what we will show in this talk is the main topic is online sampling against an adversary. And we also discussed an improved bound in online learning, and then discuss the connection between sampling and online learning. So first of all, we are interested in sampling algorithms that receive a large amount of data, a large stream. And this data cannot be handled, all of it, because it has a lot of data. So our algorithm will sample randomly a small fraction of the data and analyze only the sample fraction. An example for these scenarios are data on internet traffic, financial transactions, sensor networks, and so on and so forth. So let's give a definition of a sampling algorithm. So here we have an analyst on the right, which receives a stream of elements. And for each element, they decide whether they want to store this element or discard it. And here, for simplicity, we assume that each element is stored independently with some small probability, such that most elements are not stored. And now the analyst has access only to the sampled elements. Now, in classical streaming algorithm, the assumption is that the stream is fixed ahead of time. However, it doesn't capture scenarios in which the analyst can interact with the stream. This happens, for example, for online stores that they compute statistics on the past transactions, and using these statistics, they further decide on their inventory and in their prices, and thereby they influence the future elements in the stream or the future transactions. And similarly, network devices that compute the congestion on each link, and then based on that, they decide on what route to select for new packages, and thereby they also influence the future elements in the stream. So once we've shown that the classical assumption does not hold in many cases, let us suggest a new model that was defined by Ben-Eliezer and Yogev. And here we have an adversary that selects a stream, and the adversary can see the internal state of the analyst. And in our case, the adversary knows exactly what elements are sampled, and based on that, he can decide on what elements to select for the stream. So the adversary knows what elements are sampled. Now, once we've defined the sampling model, let's see what is our goal from sampling. And in this talk, we will be interested in collecting multiple statistics on the sample, on the stream. So for example, for shopping transactions, you might want to know how many transactions are performed in New York City, or how many comic books are bought by CS theorists, and so on and so forth. And for network traffic, you might want to know how congested is each link. So these are an example of statistics that you might want to collect. and we move to the formal model. So here we have a stream of elements and multiple statistics that we want to compute. And we want to compute the average of each of these statistics on the stream, but we only have access to the sample. So instead, we will use the average in the sample instead of the average on the stream. And our error will be just the maximum error over all the statistics, and namely the maximum over all the statistics of the difference between the sample mean and the mean on the whole stream. So once we defined our setting and our goal, let's see what we can get. And first, we start with the classical assumption of that the streams are predetermined. So here, given parameters epsilon and delta, we want to know what is the smallest sample size that is sufficient such that the sampler will have an error of at most epsilon with probability 1 minus delta. And in the classical setting, the sample size is actually an order of the VC dimension of the class of statistics that we want to compute. And this just follows from standard learning theory analysis. And that's because the sample here is just a random subset of the stream. So once we've said that for the static case, VC dimension is enough, now let's ask what can be done in the adversarial case, or whether the adversarial case is in fact harder or not. So Ben-Eliezer and Yogev showed that the adversarial case is actually harder, and they constructed the following example. So here the stream elements are just real numbers, and the goal is to approximate their empirical CDF by the CDF of the sample, and we want to approximate it in L infinity or Kolmogorov distance. And this actually exactly translates to computing multiple statistics, because just for every real number A, we want to know the CDF at point A, which is just the average of some indicator of whether X is greater than A. So we want to estimate all these statistics. And because this family of statistics is of the VC dimension 1, then in the classical case, we can do this efficiently with even a constant size sample. But what we will show is that for adversarial streams, this is in fact impossible to do. And here I'll show you the adversary that fools the sampler. So in fact, the adversary will guarantee that all sampled points will be larger than the unsampled points. So the adversary will start by showing one element in the stream, and then she will be notified if it was sampled or not. Now, if it was sampled, then the next element will be smaller. And if it's not sampled, then the next element is larger. Now, it's not sampled, the next element is larger, smaller, larger. So you see, regardless of what the sampler does, we always have the fact that the sample points are greater than the unsampled points. And in particular, unless you sample all the points, which we assume is not possible, then the CDFs will actually be very far in infinity distance. So here we showed an example where static streams is easy, but adversarial streams are cannot handle. So once we've shown a hard example for adversarial streams, we can still ask what can be done in such streams. So here, okay, we copied the results for VC dimension for the static streams, and here we have VC dimension. And now for adversarial streams, Ben-Eliezer and Yogev showed that, in fact, the sample size can be bounded in terms of the VC dimension times log cardinality of the set of possible stream elements. But this is large, too large in many cases. So the goal of this paper is actually to get tight bounds on the sample complexity of adversarial streams. So in this paper, we show that up to constant factors, the optimal sample complexity equals Littlestone's dimension of the class of function. And here, Littlestone's dimension is the analog of VC dimension for online learning. So we see a connection between adversarial sampling and online learning. And in fact, there is another connection. So our proof technique, in fact, improved the optimal guarantee given for online learning. And this resolved an open problem. So we get a better bound for online learning. It is tight up to constant factors. So now I said that the proof of this work both bound the adversarial sampling and online learning. And let's see what is the connection between the two. So you see in the middle, we have this green object that is called the sequential Rademacher complexity that was suggested by Rakhlin, Sridharan, and Tewari in 2010. And in their paper, they show that it captures the regret or error in online learning. And they also provided a bound on this quantity. And in this paper, we show that the same sequential Rademacher also bounds the sample complexity in adversarial sampling, and we provide a tight upper bound on this quantity, and thereby we also get an improved bound for online learning. Now let me discuss the proof. So the first part of the proof is bounding the sample complexity in adversarial sampling by the sequential Rademacher complexity. So don't worry, I will tell you what is the sequential Rademacher next. So here what we want to bound is we want to bound the maximum over all the different statistics of the difference between the average on the stream and the average on the sample. But because the stream is very large, we actually want to replace this very large stream with a smaller stream. And for this purpose, we will draw another sample, the yellow sample, randomly from the stream. And instead of comparing blue to stream, we will compare blue to yellow. And I just want to say that yellow actually represents the stream truthfully. And that's because the yellow sample was drawn only for the purpose of the analysis, and therefore it doesn't interact with the adversary. So in terms of the yellow sample, we can actually use the classical analysis in order to show that it captures the average of all the statistics with respect to the stream. So yellow approximate stream, therefore it's sufficient to bound the discrepancy between blue and yellow. And in the next step, we can actually discard all the remaining elements, and we now have a much smaller stream that is partitioned into blue and yellow roughly equally, namely each element is blue or yellow with probability 1/2 in this smaller stream. So now we want to massage this supermean over blue mean minus yellow mean a little bit more. And for that purpose, we introduce a random variable, sigma I, which equals 1 if the element is blue and -1 if the element xi is yellow. And then the difference of the averages will just be sum I, sigma I, f of xi divided by n. And now we assume that out of the small stream, each element is independently with probability 1/2 blue or yellow. And this gives us exactly the definition of the sequential Rademacher complexity. So we bounded the sample complexity by the sequential Rademacher complexity. And now in the next step, we show how to bound the sequential Rademacher by an optimal bound. So what is a sequential Rademacher? It's a supermean over different functions of 1/n, sum of fxi times sigma I. And in order to bound this supermean, it is sufficient to bound the sum for each statistic f separately. And this can be done using an inequality for martingales. And then we take a union bound over all the different statistics in the class. And our final bound is going to be in the order of square root of log the cardinality of the set of statistics divided by n. So this bound is good for the case where f is small or finite, infinite, but we want to get better bounds. So prior work analyzed the case that f has bounds at this stone dimension, and in order but they gave a suboptimal bound, and what was their approach? So in order to explain it, we first want to say what is an expert. So an expert is a function that gets stream elements, and for each stream element, it outputs some value. But it's not a regular function because the expert has memory and it remembers the history of the stream. And the function values given by the expert can also depend on the previous items in the stream. And now for every function of small little stone dimension and every bounded stream length, we can find a small set of experts that cover the set of statistics. And what do we mean by cover? For every stream and every function f, we can always find h, an expert from the cover that equals f on the stream. So in order to bound all the functions f, it is actually sufficient to consider only the cover of experts, and then we do a union bound over the experts in a similar way to what we did in the previous slide, and we get the bound of square root log n times little stone dimension over n. And notice here that the f can even be infinite, but always for a finite stream, we can always find a finite set of experts that cover it. Now, this bound is redundant by a factor of log n, and we want to improve over this bound. So a standard approach to remove such a logarithmic factor is to replace the cover that was given in the previous slide with an approximate cover. And what is an approximate cover? This is also a set of experts such that now for each statistic, there will be an expert that equals it in most of the stream, say in 1 minus epsilon fraction of the stream. But this expert does not have to equal f on all the stream. Now, if we can find approximate covers of cardinality sufficiently small, then we can get tighter bounds. But specifically for our case, we don't know how to get better approximate covers, and therefore prior work didn't manage to prove tight bounds for this reason, and they even gave an open problem of finding better approximate covers. Although approximate covers don't help us here, I still want to show how to get how you can get better bounds using them. So here you want to bound the maximum error over all the statistics, and we start by considering a very coarse cover. That will be our first cover, and we start by bounding the maximum error in this cover. And then we have a better cover. And in the next step, we want to bound the maximum error in the better cover by doing a union bound over the element. But instead of just considering the errors of each element in the second cover, we consider the differences between elements in the second cover and elements in the first cover. Now, in the third step, we consider differences between elements from the third cover and elements from the second cover. And we can continue like this for until we've covered all the class of statistics. And the error of each statistic will just be bounded by the sum of differences in the path containing it. And now, because the covers are getting better and better, then the errors when we go down the cover are getting smaller and smaller. So this sum hopefully would converge into a small enough value, and this will give us an upper bound. So that's how we can derive a bound using approximate covers. But as I told you, we don't know how to find good approximate covers for this case. And the solution of this paper is to relax the notion of an approximate cover. So now, while a cover is just a finite set of experts, we use the notion of fractional approximate covers, which are distributions over experts. Now, instead of wanting the cover to be small, now we want that for every stream and for every f, there will be a sufficiently large probability that a random expert drawn from this cover will approximate f. And actually, we can use a similar proof idea to prove that a fractional cover derive bounds. And because we can find good fractional covers, we can get the optimal bound on the Rademacher complexity. So, now I concluded the discussion on the bound on the sequential Rademacher complexity. And this concludes the discussion on the proof. And let me summarize what I've talked about. So we have the adversarial streaming model, and here we want to approximate multiple statistics. We showed that the sample size is approximately Little-Stone's dimension. And we also showed that we can get tight bounds in online learning. Now the proof technique reduces to sequential Rademacher complexity, and we use fractional covers to bound this sequential Rademacher. Now, what are the open problems? So we can think of maybe different models for the adversary. We can think of other sampling goals. We can, in fact, perhaps find better sampling algorithms for specific families of statistics that improve the dependence on epsilon and delta. So it's not possible for some families, it is not possible to improve, but for some of them, perhaps this dependence can be improved. And also for real valued, we can consider real valued function classes. And this was already considered in some future work, but there are a lot more open questions to consider. So thanks for listening, and see you in the session. Thank you very much.